Swayam Prabha. Digital India. Educated India.
Okay, so just very quickly, so all of you know how paging is enabled, right? And then what are the precautions to be taken before enabling paging? I taught in the class. The page that enables paging should be identically mapped. Then only the next instruction will be executed. Okay. So there is a page A1000 to AFFF. Okay. 3 Fs. And then there are, starting from B1000, there's BFFF, C1000 to CFFF. So these three are pages in the, so this is, let me call it as code page 1, this is code page, this is data page 1, data page 2. Then there is something from D1000 to DFFF, then E1000, E1000 to some EFFF, then F1000 to FFFF. So where are the page tables you have stated? Page table is from F1000 to FFFF, and E1000 to EFFF is the page directory. And this is the what you call as something like a control page, which has all your segmentation and other things. So this page should be identically mapped. This page also, this page also, this page also, this one and this one. All are identically mapped. Okay. Then every other page, the odd page should be mapped on to this one, B1000 to C1000, and BFFF, and even page should be mapped down to CF. That's how you set up your page directory and one page table. So okay, let us say this is one general thing that you can do. Then things like you can access a very big address but see that it is going to access only at somewhere in B1000 or C1000. Then jump to a very large offset but it will jump to the next instruction. Things like that you can try. And once you do this, you will also see some changes in the page table, right? That page is accessed, that page became dirty, all these things you can do. Right? The next interesting thing is you actually make one page not available and try to access that address, see that it goes to a page fault handler. And what will the page fault handler do? It will go and fetch the page, do a lot of things. That we will not do, that the operating system will teach you. The page fault handler can just go and make that bit 1 and restart that instruction. So that again you can restart and start executing that again. Okay. So you can create a page fault and make that page 1 and then come back. So these are all simple exercises that you can basically carry out and get an idea of how this paging works. Right. Very, very simple exercises. If you apply your mind, half an hour you can finish this. Not a great deal at all. Right. And the interesting thing is after that there are a set of problems that we have been cooking, right. So every semester we have been getting some new set of problems. So those problems, what he says, you can do this. Once you have this infrastructure, solving these problems are going to be very straightforward. Correct? Correct? Right? So this is what is needed out of you. So very, very simple. You get these basic building blocks, get an understanding of it, then whatever problem is uploaded in the Moodle, just go ahead and do that. And that is going to be very straightforward. See, I am telling you, while doing this, you will understand entire thing about paging. Tomorrow in the operating system course, they talk about anything about paging, you will understand what it is. How will the page fault handler work? How will this exception be generated? All these things will be known. So you have to write a page fault handler. What will the page fault handler do? It should find out which page there is a fault, and then it has to go and make that one. Right? So when a page fault happens, there are some control registers actually updated saying where that page fault, which page, you can get some ideas. Okay, just go and look at this Intel Manual 3, you will get all these ideas. Right. So you have to find out where it went wrong and go and make that bit 1 and then restart. Then it will work. Okay. So in terms of this, please look at, see, in a page directory entry, right? The first bit is a valid bit. If you have 1, that means all these things make sense. If you have 0, nothing makes sense. So this is a page directory entry, and this is a page table entry. So you could have also 4 MB pages. In large databases, they will, now we are talking of 4 KB, we can have the page size to be 4 MB also. So we will not bother about 4 MB here, we will just do 4 KB, because let us try and understand. So these two, whatever page, this is 114 page number of this volume 3, essentially talks about how the page directory entry looks like, and this also tells you how the page table entry looks like, right. So this is what is pointed to by CR3. Okay, this is what is pointed to by CR3, the start of this page directory, and this will point through this. So every page table, its address will be there in the PDE entry. When the first bit is 1, as you see here, I am just rotating here. Okay, when the first bit is 1, then it essentially means that this entry is valid, otherwise it is invalid. And what are these things? Let us go one by one very quickly. Read/write. What is R/W? Where is it? Read/write means the first bit is 0th bit, which is called bit 0, is the present bit. The first bit is read/write. If 0 means writes are not allowed, 1 means write will be. Anyway, a page can be read for sure, but I may not allow you to write. So for example, where do you want, in the absence of segmentation, suppose I have an architecture where there is no segmentation, where do I want no writes? Code segment, correct? Code segment I don't want to touch, or I could have some parameter segments which I want to preserve. I don't want the program to come and corrupt it. So if I make certain segments as read only, then lot of security issues can be handled. The second bit is user/, if 0 means user mode access or not allowed, okay, otherwise it will be allowed. User mode means 3, supervisor means 0, 1 and 2, right, or 0 is supervisor, 1, 2 and 3 are user. I don't know, you just check section 4.6. We will go there, but no, it will take time to come back, okay. Okay, section 4.6 will tell you. I think user is 1, 2, 3, user is 3 and supervisor is 0, 1, 2, okay. And okay, this page level cache level write through I will just check later, I will just tell you later. Just forget about 3 and 4, we will deal it when we do the cache. Fifth is accessed. After I loaded, did I go and read or write into it? That is this. Sixth is our famous dirty bit, okay. Now then there is something called 7. 7 is page size, okay. Page size must be 1, otherwise this entry references a page table, okay. Forget this also, just make it 1, okay. We will discuss about that later. 8 is global. If CR4.pg is 1, determines whether the translation is global, otherwise ignore. This also you ignore, as because we are not going for 4 MB pages now, okay. And there are some 9, 10, 11, 3 bits which is ignored, which you can use. Then there is page address translation, again you can forget this. Bit M minus 20, 30, 32 of physical address of 4 megabyte. So I will forget. Okay. So these are the bits you should know for sure. Okay. In this page directory entry and page table entry. Okay. Fine. Right. So okay. So you set up this page table and start working on it. This is easy. This is what you should see. Table 4.5 is what you should see for 32-bit, whatever you are using. That was, I think that was for a 64-bit, right? That's a 4 megabyte page. So we are doing 4 kilobyte page, sorry. So this is what you should do. Okay. And this is for a 32-bit entry. Okay. So there are a lot more of this paging things, but then that will come under advanced computer architecture, because we need to know a lot more about a operating system to appreciate things. So we'll stop at this stage to give you a loop into operating system. Once you start studying operating system, there you may need so many other things. You come back to arcade and learn lot of things. There's no point in learning so much of Intel also. Okay, Intel is not our cousin or something. Okay, so you learn something about thing to just understand what is how paging works. The foundation will get, but we will not focus too much on Intel. There are other processors. Right? As I told you, right, 99% of the computing device in this earth now uses ARM. Okay, so Intel is only 1%, because all computing devices are mobile devices today. Right? So we will not basically break our head so much. But nevertheless, we should understand how it works. And this is a very nice case study. But nevertheless, if you really want to bring a secure system, I still believe why I'm still teaching this, because down the line, if I really want to build up a hardware security, okay, then it's very, very important that I think Intel will succeed that. This level of double security, 3-tier security will be. Right? You have a security at segmentation, security at paging, and then 4 levels there. And then I have LDT, GDT type of security. Then from that, then paging. Okay. So see, dead codes. What are dead codes? Dead codes are those which you cannot actually, when you execute the program, right, you can never get that part of the code to execute. These are all potential, worms or whatever, malicious code, because in some specific input pattern, that fellow will start executing, right? So that's why. So we really don't know, by just looking at a program or by even executing a program, we can't do a security analysis of that. Because there could be some hidden part of the code and some combinations of the hidden part of the code, some composition like function 1 then calls function 2, then function 3, then the behavior will be different. If I call function 1, then function 3 and then function 2, the behavior will be different. Right? So I could compose it in different way and get different behaviors. So these are some very interesting things that could happen. So security wise, I think this level of protection will be extremely okay. And then I don't know what we will be learning in operating systems, but one of the important concepts that we need to learn is about capability based operating system. What is a capability based operating system? A capability based operating system is one where for every object in your operating system, you have certain access rights, and for every object, its relation with every other object is very well defined. Okay. For example, process is an object. Now, I take one process, say some daemon, right, HTTP daemon. Right? You know what an HTTP daemon does, right? It basically runs the HTTP server, right? So if I take the mail daemon or something, so HTTP daemon has some access. So there are several resources. I have CPU, I have memory, I have peripherals, I have ports, I have Ethernet cards. So there are several things there. So and then within part of your system itself, there are some specific parts of your code like file system management, process management, etc. So this process, what is its relation with every other process? I need to have that well defined. It should be very well defined. If it is not well defined, then that's where the lapses start. Right? So this fellow is not supposed to go. The HTTP daemon is not going to go and touch some part of your super block. Why should it go and access your super block of your disk? There's something called super block. You learn in voice course. Why should I go and access? Right? Suppose I say it cannot access, and that rule is implemented, then your security of your operating system can be much more effective. But that type of capability based OS, we are not in a position to build. But what I believe is that if you go as rigorous as Intel's x86 plus this, we can build a really capability based OS, wherein we can enforce these policies and trust on the hardware god to implement it for us. Right? So I put these policy, I put these rules, who will implement? I am very happy if the hardware does it for me, rather than the software, because hardware is immutable. I have designed the hardware, I can't go and change a transistor and do anything. Software is immutable. So that is one reason why I still believe that x86 will be sort of the hardware when you want to start building those type of fancy or those type of really secure operating systems. Doubts?
So,
Yeah.
so does any of the current OSs uses all these features of internet?
Linux uses x86. Actually, one abridged version of Linux is even there, 8,000 lines of code, which you can see. If I ask you to see 2 million lines of Linux code, you go mad. At x86, go and look at x86. So this is the whole thing given by. So GitHub is there. Then you can open x86 here. Oh, see, beautifully they've done. So this is very well written, indexed code. So you will have first 10 pages or 12 pages as see lot of empty spaces, and here it starts your memory layout. Can you see LGDT? Okay. See, so LGDT, ASM is assembly, so they are using LGDT. Same. LIDT, LTR, load task register, clear interrupt, STI, move instructions, GS register, all these things. So that means what? Linux uses lot of your assembly instruction. I'm just proving it. Okay. Just don't think that we just did it. See, CR2, CR3, everything is used. Okay. So if you want to actually learn, see this is see your segment descriptor, limit, base, then type, and somewhere so limit 19 to 16. So this is your segment descriptor. So these are completely used. Okay. So if you can actually go through this, now it will all go to this is your context of your process task state. Okay. So see, you have entries for all your registers, right? EAX, ECX, EDX, EBX, and then your CS, SS, DS. I told you, right? CR3. There's an entry for CR3 also in your task state, right? So for every task, okay, for every task you can have your page directory base. I told you in the morning, right? So this is a context of your process, right? And it goes on. So the entire course. This is the first line of code, boot asm.s. Okay. So the first two will be some entry here. So it goes. Okay. So this is how you enable paging here. See, move L CR0 EX, RL move as EX to CR0. Right. So this is the point where you are enabling paging, turn on paging. So whatever you did now, the operating system also does. Okay. So I'm just giving you a one-to-one mapping of what is happening. Okay. Then it jumps to AX and so on. So what you did exactly in your lab, right, for enabling paging, that is there in line number 1153 to 1155. If you understand x86, then you can go and directly play with the kernel. Right? There are some 10 exercises here. You understand all the 10 exercises, you can go and play directly with the kernel. See, class, lab 1 to lab 7. After this, right, after your current course, on the operating system course, the best thing is to take x86, understand it completely, and take this, compile this into assembly and boot your, now you are booting with that USB, right? Now boot with x86 and see how it is working. And then go and change some scheduling algorithm and see how the counter works. So that will be the real josh. That means one full semester you should do only operating system. You not have compiler, networking, all these things. Right. But then if you do that, you will become real OS Dada. Okay, that is something, because you really got a machine to boot from scratch and come up. So go and read this x86. This is real operating system. Okay. So yes, you are only using trap gate, right, so far?
He asked him to use trap gate, but the template had a task gate.
So I see. You should have used only trap gate. You have used task gate because the template had it.
You are not able to implement the trap gate, so we went.
Why? What do you mean by implement the trap gate? Just you have to go and make that IDT entry as whatever. You have to just change the bit type that. That's all. Then it becomes a trap gate.
But it is not.
It didn't work. Send the code. Send the code that doesn't work. See, task gate will be taught in assignment number 5. Trap gate, and I will also explain why task gate is necessary in the context of an interrupt service routine. That I will explain. There is something called double fault. Okay, and for that we need to have a task gate. But for all practical purpose, for your interrupt service routine that you have written as a part of your third assignment, task gate is trap gate is enough. Trap or interrupt gates are enough. Task gate you should not use. Meaning you can use, but that's
We use interrupt gate to make our code, but if you want to do interrupt in a PL0 code, it works, but if you do it in PL1 code, then it's not working.
Because your interrupt gate, the privilege level of your interrupt service routine.
We set it to 3. So all this.
You set it to 3, and what was the code segment privilege level? So the interrupt descriptor table was pointing to a code segment, right?
Yes, sir.
What was the privilege level of the code segment?
0.
So how will it work? So it will not work. So, right? We will teach you about task gate in the 5th assignment. Right. So a trap gate or an interrupt gate should have worked in your third assignment. If it didn't work, then send us the code. I will clarify it.
But the privilege level of the entry of the IDT, it is used such that the code segment that is trying to access it should have the privilege level less than that of the entry of the IDT, right?
Right. So there are several issues here. I can only talk about, I'll give you a brief of what is happening. See, if I am a privilege K code, then my stack has to be privilege K. Stack cannot be K plus 1 or K minus 1. So this is very important. This is what x86 will ask for. So if I am a privilege K code, my stack also will be privilege K. Okay. So if I am a privilege 3 code, the stack I am going to use should also be privilege 3. Okay. It cannot be privilege 2 or 1. If I am a privilege 2 code, the stack should also be privilege 2. It cannot be 3. It cannot be 1 or 0. Please note that. It is unlike a privilege level 3 code can access a code segment of privilege level 3 and privilege 2 can access 2 and 3. But for stack, if I am executing a privilege 3 code, the stack should also be privilege 3. Right? It cannot be privilege 4, or the descriptor should have privilege 3. So this is how x86 is defined. The reason is as follows. Okay. Now let us say I am executing a privilege level 3 code. There is one instruction which generates an interrupt or trap. Okay. Okay. Now what will happen is this will go to the interrupt. So let me say it is giving you interrupt 13. So I go to the IDT table, I go to the 13th entry, and here I have a code segment selector, and then there is some privilege level here. This privilege level should be at least 3, then only this fellow, if it is PL3, this should also be 3. If it is PL2, then this should be 2 or 3. Okay. Then only this interrupt itself will be executed. Now this will point to a code segment. If this code segment is at privilege 0, okay, this code segment, this is a selector, right, this will say some 15 or something. So 15th entry in your not in your IDT, this will be a 15th entry in your GDT or LDT, depending on that. There you will go, here there will be a base limit, etc., and then there will be a privilege level. This privilege level is 0. That means now when a 3 code is executing, because of an interrupt I am going to execute a privilege level 0 code, right. So what you will do is, you will have a stack defined for every process that I am creating. I will have 3 stacks or 4 stacks. Every process I am creating, I could have 4 stacks. One stack is at privilege 3, another at that privilege 2, another at that privilege 1, another will be privilege 0. If this interrupt service routine is at privilege 1 or 0, right, then this stack, either the 0 stack or the 1 stack will be executed, depending on what the privilege level here is. So for all the processing of your interrupt service routine, this PL3 stack will not be used, your PL1 or PL0 stack will be used, depending on what the privilege level. So why is this done? Because I do not want the system stack and the user stack to be the same. I am a program, I am asking for a service from the operating system, that is called a system call, right. I say printf, scanf, I go and ask many things from the operating system, right. In C there is a command called system, right. Are you aware of this? System, and I can put whatever I want here. So essentially I go transfer control to a system. Malloc, for example, is a system call, okay. fopen is a system call, free is a system call, okay. So when I call that system, the system call should not execute on the same stack as mine. Then what will happen after I return, I have access to the stack, right. I as a user level process has access to the stack. So I will start knowing more about what the stack contains, right. So I will start having more ideas about what the stack is trying to do. And so I do not want the privilege level 0 code to execute on the same stack, because after I come back I will have access to all that has been done. In the imagine password, right, this will take your password, do a hash and then compute there. So all those computations, all those residue things can be there. So that is why x86 says that you are a user fellow, you use a stack. When you want to go to a privilege level 0, when you want to execute interrupt service routine, when you come up, right, when you are actually spawned as a process, when you start executing, you will have your stack, then there will be 3 more stacks. Suppose I am at privilege 3, there will be 3 more stacks, privilege 1, 2 and 0, 1 and 2. If the interrupt service routine is going to be for 0, then it will use your PL0 stack. As a process I have 4 stacks, and my PL0 stack will be used by the PL0 code. If my interrupt service routine is PL1, for example printf, fprintf can be PL1, while malloc can be PL0, okay. So or some exit can be PL0, right. So I will have PL1, PL0. So depending upon what my system call is, which privilege level my system call is, that corresponding stack can be used, right. So this is how, so what would have happened when you had used an interrupt gate and your code segment was at PL0, your 0 stack would not have been set correctly, and that is why your interrupt gate or interrupt/trap gate would not have worked correctly. You are getting this. So when a process is spawned, we will when I am doing the task switching, I will cover it in great detail. When a process is spawned, these stacks should be set. Once these stacks are set, when I do an interrupt, then these stacks will be used. Now what I want you to do is, you see there is an interrupt generated, go and see what is the interrupt number, go to the code segment, go and find the privilege 0 of that code segment, privilege level of that code segment. If it is 0, then you see whether there is a 0 stack set. Where will that 0 stack set? It will be set in a task state segment, right. So we will come to it. First to find out what is the privilege level of the interrupt service routine, and then you send me the code, we will debug and send you back. Are you able to follow? Okay.